All right. Okay, so the last time, in our last lecture, we have first introduced the concept of a recurrence or recurrence equations. And we use that as a tool to represent the running time for merge sort. Okay, and this merge sort is the first divide and conquer algorithm that we come up with within this course. And now let's have a brief review about the process, how we solve the sorting problem with a divide and conquer approach. Okay, so what we do is to given an input sequence that we want to sort, we divide it into two subproblems, right? And each subproblem is half the size of the original size, okay? And for simplification, we assume the length of the input or the input size is always the power of 2. So we can do basically infinitely do the split infinitely. So each split will result in two even numbers. Okay, that is just for convenience of the analysis. So the first step is to compute the middle point of the array, right? Compute the middle index, okay, to split the two constraints, to split the original sequence into two subsequences. And then in the conquer step, we will call the function recursively, okay? So this recursive call is basically a characteristic of the divide and conquer algorithm, okay? So we will basically call the function itself on top of the two sub-inputs or the two subsequences. Because each subproblem is now half the size of the original size, so we can use the same function, capital letter T, but with a smaller inputs, which is n over 2, okay, to indicate that, okay, so this time the input size is half the size of the original size, okay. But remember that we have two subsequences, so there's a 2 times T of n over 2, okay. Alrighty, and the third step is to combine the results from all the subproblems after we have solved them recursively. Okay, so we already have information that the merge procedure has Big-Theta of n running time, right? Because the merge procedure is basically a for loop, right? That goes through all the elements in the go through all the positions within the input sequences. So there's no it's not that complex in terms of running time. So we can basically represent the running time of the merge procedure as a linear function. All right. So combining, like taking all these 3 steps together, we can use this recurrence equation to represent the total running time of a merge sort problem. Okay, and we further simplify it into this form by ignoring the lower order constant term here. Okay, so the method that we use to solve this recurrence. Okay, so first of all, this equation is not the final form, is not the final outcome that we desire. So we want some clearly defined analytical solutions for the T of n, right? We want T of n as something that we know, but this form is just an intermediate form. It is some middle steps. We need to solve the T of n based on all the information we have in this set of equations. And the method we use in the previous lecture is that we can draw the use a tree-like plot to visualize the recurrence equations. Okay, so how do we visualize it? Is to start from the top node, which is also the root node of a tree. Okay, and the root node has this c times n as its value in the root node here. Okay, and so this is the first split because there's three components basically. There are 2 times t of n over 2 and a c of n and a c times n. So we can basically write that 3 parts into a triangle and draw a tree-like structure. Okay, so because the subproblems can be further splitted as we call the functions recursively, so this t of n over 2 can be split into more branches. Okay, and the nodes, the values of the nodes also becomes smaller. It's basically half the size of the value of the previous level. Okay, so it's c times n over 2, c times n over 4, and so on. Okay, that's basically how we visualize the tree. Okay, and after we have plot the tree, we can further examine the tree by looking at the summations of each level. And we are quite lucky to have found that each level have the same summation, which is c times n. Okay, so all we need to do is to compute how many levels are there in the tree. Okay, then in terms of the level of trees, we have, using some calculation shown here on the left, we can find that the number of levels is this quantity, logarithm of n plus 1. Okay, so for the previous, so for this, how we get this quantity, I hope you have gone through it yourself on the paper, and also watch the videos and the slides yourself until you have understand it. Okay, so we will come to that later when we officially introduce divide and conquer approaches. Okay, anyway, once we know the number of levels and the summation of each level, then we simply times these two quantities and we will have the total running time. Okay, and it can be represented by this quantity, this equation. Well, it's n times logarithm of n times c plus a linear term. And since compared to the first term, the linear term is a lower order term, okay, then we can just keep the higher order term, which is n times logarithm of n. Okay, and we also use the Greek letter notation Big-Theta as a generic representation. Okay, so this is different from insertion sorts, this running time, mathematical equation expression of running time. And obviously it is better than the quadratic running time. So if you plot these two functions, if you plot the quadratic function n squared versus the n times logarithm of n yourself, then you will see that the function that has a logarithm term in it grows slower. Okay, and the difference between these two functions becomes larger as the n increases. Okay, which means if we have a small input size, say if we only have 100 numbers to be sorted, then probably when we compare an insertion sort versus a merge sort, there's no significant difference. Okay, they basically return the result instantly. Okay, but things will be more different if you increase the input, say to 10,000, 100,000 numbers. right? Then that's as the n increases, and the difference between the two functions will be much more significant. Okay, and with the help of the logarithm term, merge sort, the running time for merge sort will not increase ridiculously fast as compared to insertion sorts. Okay, and this comparison of the running time is the basis of why we claim that merge sort is a superior algorithm compared to insertion sort. Okay, but that doesn't say that insertion sort is something we should totally abandon, and or merge sort should be preferred in all cases. Okay, because this is only the analysis with respect to running time, right? That's just one aspect of computational resource. Yeah, so I think William has mentioned good points that the cost for merge sorts largely exists in the memory cost. Okay, so remember in the algorithm, we need to allocate two chunks of memory space to store the first half and the second half of the input subsequence in a merge in a merge procedure. Okay. Would the space complexity be Big-Theta of logarithm of n? I don't think it's logarithm of n, because we didn't do the analysis, because say we have the inputs size, which is n, right? That's a good question. So Jamshid raises a very good question. So the input size is n, and the logarithm of n is usually the number of the heights or the number of levels in the tree structure. Okay, so if we go back to the previous slide, say given this tree, you see the inputs. So you can think of the lowest level as your input, right? That's n numbers. So given the inputs of n numbers, then there are roughly logarithm of n that many levels in a tree. Okay, but that's just the number of levels. But for each merge step that occurs in each node here, we basically need to cost some memory to store the segments of that length. That we need to allocate that many memory space to conduct the merge procedure, right? So roughly, if we want to roughly estimate the memory complexity of the algorithm, I think it should have the same level as the Big-Theta of n times logarithm, or logarithm of n. Yeah. So because each merge steps is basically also takes linear amount of running of memory space, which is similar to the running time analysis. Okay. So yeah. So which is a significant extra memory cost if you compare it to insertion sort. And the insertion sort is totally in space, right? We didn't it doesn't cost us anything in the additional memory space. Yeah, right. We can see that there's a trade-off in memory. No, we basically need to have a trade-off between memory and running time complexity. And for most of the practice and questions that we are interested in, we focus on the time complexity. Okay. we usually, if we have sufficient amount of memory space, we usually want to trade running time for trade memory space for sufficient for increase for improvements in the running time. Okay. All right. So then I think we are pretty much done for this getting started example using sorting algorithm as an example. So we have a quick introduction to introduce the Big-Theta notation, right? And this notation is something that we call asymptotic notation, which is to describe the properties of functions, okay? Say T of n equals Big-Theta of n squared. It basically, in plain language, we are claiming that the T of n function grows as fast as the quadratic function n squared. And this T of n equals Big-Theta of n times logarithm of n would basically claim that it grows as fast as the n times logarithm of n function. And today, we're gonna officially introduce how we define those Greek letters, how we define the asymptotic notations to describe the growth of a function. Yeah, I see Brandon's question. So we can actually go back quickly. And C is just a constant number, right? Because C is a very is a constant that we arbitrarily define. So this C means that when we reach the smallest case in merge sort, which is the input sequence of length 1, okay? When we only have one element in the input sequence, the cost is constant because we just return the function. We didn't do anything, but that is still some constant cost, okay? And we will have n of such basic input elements, okay? So we didn't do the infinite split, okay? It's not infinite split because with one split we have c times n divided by 2, and when we split twice we will have c times n divided by 4. Okay, so if after I times of split we will have c times n divided by 2 to the power of I. Okay, and say, but we're gonna stop. We will not do the infinite split. We will stop once we have the smallest case. So if we let c times n divided by 2 to the power of I to c, that is our smallest case. Yeah. So that is our the terminating condition. So yeah, we will never go beyond this step. Okay. And by solving this equation, we will have that I equals logarithm of n. And so this quantity I equals logarithm of n means that we can at most do logarithm of n many splits. We can only do that many levels of splits, right? If we go one level further, we need to divide one's elements into 2/2, which doesn't make sense in this case in the sorting problem, right? Okay. If you have further questions, I would encourage you to read this slide, the left parts, and also in the textbook. I think it's also in the chapter of getting started. There's a more detailed description of how we do the split in the tree plots. All right. Let me switch to a new slide. Okay, pause my recording. Okay, so for this lecture, hopefully we can finish it today. We will talk about the growth of functions, and we will officially introduce the mathematical definitions of the Big-Theta notations that we use. And other than the Big-Theta, we will also introduce the other two notations, big omega and the big O. Okay, but I think these notations, they are very closely related, and once you have understood what big theta means, then it's quite easy to pick up the meaning of big O and big omega. And that's big theta, big O, and big omega, and correspondingly we will have lowercase small omega, small O, and yeah, we have small O and small omega. We will also introduce that. Okay, but the three basic, the most basic three types of asymptotic notations are big theta, big O, and big omega. Okay, let me open the chat. Okay, let's get started. Okay, all right. A short review, right? We have done that just a moment ago. So we have two different functions to describe the running time for insertion sort and the merge sorts. So the most straightforward way is to plot these two functions and compare to find out which one grows faster, right? So if we do a extreme comparison, just like what we did in the very first lecture, we want to do a very unfair comparison. In order to show the superiority of merge sorts, we will let insertion algorithm runs on the really fast computer, so the constant is very small, right? And we let merge sort run on the slow computer, which gives a 100 constant factor. Okay, so this is already very unfair. But so now let's see how the functions grow. Okay, if we randomly, if we generate some numbers and define the functions in the computer software and plot it. So at the beginning, so if the input is pretty small, say lower than 500, then the merge sorts in green color obviously grows. It has greater values, right? It has greater values. But from the trend of insertion sorts in red color, okay, so the insertion is in red, its curve is like grows much faster than the nearly linear linear curve of merge. Okay, all right. If we look at larger input size, then when n equals 1,000, then the two functions, they already overlap. They already hit. They already have the same outputs. Okay, so it's easy to imagine if we use even bigger values, then the insertion sort will have greater costs, even if it has much smaller constant factors. Okay, so that again shows to the design of algorithms. It's the growth of the function that really matters. The constant factors in the algorithm is not the determining factor, because our input can be very big. Our input can be infinitely big. So ideally, we want to consider the case that inputs can be infinitely big. And that is something we need to keep in mind when we compare the efficiency of algorithms. We need to always consider the fact that the input can have can have really large inputs. The input can have really large values. Okay, and that's why we will need to use the concept of asymptotic efficiency. Okay, so this term asymptotic efficiency basically is about the property of a function when the input of the function grows infinitely big. Okay, it is used to analyze the efficiency of algorithms. Okay, So we want to determine the order of growth for the target function T of n, okay, because it is really what matters, okay. The symptotic term means that we want to study how the running time, how the function T of n increases with the input's size when n is approaching infinity without a bound, okay, when n increases without a boundary, okay. That is the property we want to analyze. It is not within a small region of inputs, say below 100, below 500. We are not considering those special cases, but we are considering the general cases that the input can be infinitely big. All right. So if an algorithm is better when the n, when the fact when the infinite values, when the infinite input sizes are considered, then we say an algorithm is a better choice. Okay. If we don't consider those infinite the input size that can infinitely grow, then our analysis is incomplete. Okay. All right. So the first notations we're going to look at is the Big-Theta one. Okay. So in this, I listed the three notations here: Big-Theta, Big O, and Big Omega, and they have the same. They are defined in similar ways. So we will start with the Big-Theta first. Okay, I think with Big-Theta introduced, the Big O and Big Omega are quite easy to understand. So first of all, these notations they apply to functions. Okay, so we can say that a function belongs to Big-Theta of something, right? But we cannot say a number belongs to Big-Theta or a number belongs to Big O. So these are the notations applied to functions, okay, and they describe the asymptotic properties of functions, okay. And in this course we usually use them to describe the running time, but in practice it's always doable to describe them, to describe the memory costs, okay. So in Big-Theta, now let's officially look at the definition. For a given function g of n, which can be an arbitrary function, okay, then we will denote by Big-Theta of g of n to a set of functions, okay. So it's the mathematical notation, the term set, okay. So it's a set of functions, and when we define a set, we will use curly brackets, right? We will use a pair of curly brackets, and within the brackets, it's the definition for, or it's the condition that each element in the set must satisfy, okay? Because it's a set of functions, then the elements in this set are all functions, okay? So for example, f of n is one element in this set, and f of n must satisfy the condition described after this column, okay? So what is the condition? The condition says that to each element in this set, there exists positive constants C1, C2, and N0, such that f of n should be greater than or equal to C1 times g of n, and be smaller than or equal to C2 times g of n, okay? And these, of course, they are greater than 0, okay? For all n that are beyond n0, that are greater than or equal to n0, okay? So it basically tells one thing, okay? It basically tells that f of n, the range of f n, the value of f of n can be is somewhere between the lower bound and upper bound described by G of n. Okay, and all the functions that satisfy this property can be denoted by the big theta of G of n notation. Okay, so in the language, in a more plain language, we would say that if a function belongs to the big theta of G of n, then there exists positive constant C1, C2, so that the resulting C1 times G of n and the C2 times G of n, they form the lower bound and upper bound that kind of sandwich the function in the middle. Okay, as long as n are sufficiently large. Okay, so this n0 is also important. Okay, so for all the n that's greater than n0, that means n can increase infinitely big, right? So that is somehow describes the asymptotic property. It is not a temporary property that only holds within a region. It basically applies to an open region as long as n is greater than n0. Okay. Okay. So strictly speaking, when we say a function can be described by a big theta notation, we need to use the belong symbol, right? Because the big theta is a set, okay? But usually we already see that in the previous slide, in the previous chapter, we said T of n equals something, okay? So technically speaking, this is not strictly correct, but we are tolerant to that. We can say that T of n equals big theta of G of n squared. Okay, it basically the technical meaning is that T of n is a member of such a set of functions. Okay. All right. So in the next slide, we will have a plot that shows what big theta means. Okay. So I think these plots makes it easier to understand the notation. It basically says that as long as the input size n is sufficiently big, then the value of f of n lies between C1 times G of n and C2 times G of n. Okay, as long as we can show that, as long as we can find the C1, C2, and n0, then we can kind of prove the big theta notation. Okay. So another term for big theta is that we say G of n is an asymptotically tight bound. Okay, it's tight because it's not just upper bound, it's also a lower bound. Okay, so with the lower bound and upper bound, then the region is quite clearly defined. Yeah, so the n0 is also a critical point we want to find, because in this case, for n's that's smaller than n0, then the f of n falls below C1 times G of n, right? So that doesn't matter, okay? Because the whole definition of big theta requires such a n0 to exist, okay? So as long as we prove that for everything, for any n's that's greater than n0, the f of n is always between C1 times G of n and the C2 times G of n, then we prove the big theta relationship, big theta notation. Okay, it's okay that before n0, this property, this inequality doesn't hold. Okay, that's okay. Okay, the most important thing is that we find such a point, we find such an n0, and we also find such C1 and C2 make the whole inequalities to be valid. Okay, so this is a intuitive picture of big theta notations. So now let's see yeah, and a supplementary condition is that the f of n of g of n themselves, they must be non-negative when n grows really big. Okay, if there's negative values, then the definitions of big theta is not satisfied. Okay. So in the in the following several slides of concrete examples of big theta notations, I'm going to show how mathematically we can prove that we can prove the big theta notations for concrete examples. Okay, so the first example is here. Okay, so given this quadratic function, f of n equals 1/2 times n squared minus 3 times n. So what if we want to show that this function belongs to the big theta of n squared? How do we do that? That is a question we need to prove using the definition, official definition of big theta. Okay, we need to justify it. According to the definition, we need to find the positive constants C1, 2, and N0, okay? And such that the target function here, I think we can ignore the C here, okay? Because there's no C in the function here. The target function should be between C1 times N squared and C2 times N squared for N that's sufficiently big. Okay, as long as we can show that, then we can claim that the function belongs to the big theta of n squared, right? So what we can simply do is to using this inequality. Oops. Using these two inequalities, and we divide all sides, both sides, by n squared, and it will yield us this new inequality, right? So the n squared are gone, right? Here, n squared, the n squared are gone, and we have a new inequality. So C1 should be smaller than 1/2 minus 3 over n, right? And C2 should be greater than this value. So there's a bit of conversion here. Then we simply need to choose any constant, because we have the freedom to choose C1, C2, and N0, right? All we need to do is to find such a case that satisfy our constraint, that satisfy our requirements. Okay, and our requirement is just the inequality. Okay, because we know that this part in the middle, it must be smaller than 1/2. So as long as we choose any constant that's greater than 1/2, then this less than or equal to inequality must hold, right? That's something we can see quite straightforwardly, right? And the other case, we know that when n is bigger, okay? So how do we say that? So when n increases, right? So for example, when n equals 6, this whole thing in the middle will be 0, right? And when n equals 7, then this part in the middle will be greater than 0, right? And all we need to do is to find the C1 that's smaller than the minimal values of the part of the middle equations of the middle term. Okay, because the middle term will increase with n. Okay, when n approaches infinity, the middle term will approach 1/2, right? But it's always smaller than 1/2. So we can find the points in which the middle term has the smallest positive value, which is when n equals 7, right? When n equals 7, this middle term is 1/2 minus 3/7, which should give us let me see, 1/14. Yes. Okay. So as long as we choose C1 that's smaller than 1/14, then the left inequality also holds. Okay. And for n0, then n0 is 7 in this case. Okay. So now we can determine the C1, C2, and n0 so that the inequality will hold. Then we're done with the proof. Okay. Right? That's basically required by the definition of the Big-Theta. We need to find C1, C2, and N0. Okay. Okay, I think this example can be extended to a more general case. Okay, from this particular example, we can see that the linear term can be ignored, right? And in a more general case, when we have higher order terms in the function, we can always ignore the lower order terms to describe the asymptotic property. That's the first case we will see. And let's look at the second case. Okay. So let's see how we can ignore lower order terms. Okay, so this is a follow-up for the conclusion for the case 1. So the choices for C1, C2, and then 0, they are not the only one. Okay, so we choose in this proof, we choose C1 equals 1/14 and the C2 equals 1/2, okay, and equals 7. Then of course we can say that C1 equals 1/15 or C2 equals 1 or n0 equals 7. There are multiple choices of the C1, C2, and n0. The point is that we want to we want to prove the existence of of these quantities, of these constants. Okay, it is the existence of these constants that really matters. Okay, and the actual values determine on the coefficients of the actual functions. So when the functions when the coefficients change, then the corresponding values for C1, C2, and 0, they also changed. Okay. All right. Now let's look at the second case for higher order functions. Okay. So we basically, let's see, the question asks us to verify the cubic function 6 times n cubed or n to the power 3 does not belong to the Big-Theta of n squared. And this is intuitively true, right? Because we know that a cubic function grows faster than a quadratic function. Then how could it be bounded by a quadratic function? So in this case, we're gonna see how mathematically we can prove it. Okay. So suppose that there is a C2 and n0 exists such that 6 times n cubed is less than or equal to C2 times n squared. And it holds for all n's that's greater than n0. Okay, so this is by the definition of Big-Theta. Okay, and then if we divide it by n squared, it will yield n should be smaller than C2 over 6. Okay, then we will have a contradiction, right? Because n can be arbitrarily large, then how can we limited by C2 over 6. So apparently this doesn't make sense. So the higher order functions cannot be bounded by the Big-Theta notation of a lower order functions. Okay. This is a second example. Okay, so let's see a more generic quadratic function. Well, it's not a more generic function, but we still have concrete numbers in it, but it's a bit different from the first quadratic function. And let's look at in this more special form of quadratic function, how do we do the proof? Okay, well, so I want to say one thing about the proof. So it's not our goal to learn how to prove the Big-Theta and the big omega notations, but the practice of try to prove some notations is to truly understand the meanings of this big theta, for example, big theta and big omega, big O in the future. We really want to know the mathematical meanings of those terms without using them just directly without any thinking. Okay, so the proof is to help you understand the relationships between the boundaries and the target functions. Okay, so let's look at the f of n again here. So we want to show this f of n is bounded by the big theta of n squared. Okay, so we need to find the c1, c2, and then 0, right? By the definition, we want to show that. Oops. I just messed up with the animation. It doesn't matter. Let me draw the parts here. Okay, so this is our goal. Let's look at this part first. Because we want to prove the Big-Theta notation, we want to find the C1 and C2 such that the target function is bounded by the upper bound, lower bound for all n's, right? And the inequality becomes this if we move the term from the left to the middle and from the right to the middle. Then we basically have two inequalities, right? So we need to have C1. So if we observe the red inequality, it's a quadratic function, right? It must be greater than 0. So how can a quadratic function that's always greater than 0 when n can be arbitrarily big? That's only possible when the coefficients for the quadratic term is a positive number, right? Only when it's a positive number, then the curve is a bow shape facing upwards, right? It's indicated by this red curve. Okay, so only when the coefficients 1 minus c1 is greater than 0, we will have such a possibility, right? And in which cases can a quadratic function be smaller than 0 whenever, no matter how n can be arbitrarily big? And this inequality is also only valid when the coefficients 1 minus c2 is smaller than 0, right? So in mathematics, we can have those conditions inferred. Okay, so by these two constraints, we will have that C1 should be greater than 1 and C2 should be greater than C2 should be greater than 1. Okay, so that becomes the condition that we select those values. Okay. Oh, so those zeros are from this inequality, right? So if you move this C1 to the middle term, then the 0 is here. We just move the quadratic terms around in the first inequality. Okay, and so now it becomes we're kind of converting the problem into a different problem. Okay, so because when we draw a quadratic function in a two-dimensional space, we can have its we can have two roots for one quadratic function, right? And also for this one. So because our n can be arbitrarily big, then as long as the n is greater than the larger roots of these two equations, then we can have the inequalities satisfied. Okay, so that is another information we want to use. Okay, so the good news is that as long as we have C1 and the C2 satisfying this inequality, we can choose arbitrary values for C1 and C2. Okay, say we can choose the C1 and C2 that are convenient for us to solve the roots for these two set of equations, for this set of equations. For example, we can let C1 to be 1 over 4 and C2 to be 9 over 4. Okay, then we can solve n0 to be 2. Okay, so basically we can claim that as long as C1 equals 1 over 4 and C2 equals n over 4, and then n0 equals 2, then for any number n that's greater than n0 equals 2, we will have the equations. We will have the inequalities satisfied. Okay, so ultimately, we want to prove this inequality. We want to find the C1, C2, and N0s that satisfy this inequality. Okay, and again, this gives us a similar conclusion to the case 1. When we have a quadratic function n square plus 2 times n plus 1, then we can basically ignore the lower order terms and simply use Big-Theta of n squared to describe the asymptotic notations. Okay, so this slide might require some time to get connected. So I hope maybe you can spend some more time after the lecture is over to try to calculate it on paper for yourself. And let's proceed on to the.
Oh, Professor, I got a question real quick. So I'm like following lecture like through the slides, and like so instead of like the last line, it's like n not equals 2, it's like n not equals like max to absolute value a, and then so what? How does should I be following this one like that's the one you're showing right now, or the one that's on the slides? Just I'm kind of confused on that.
Yeah, you can try to, for example, because it says here, as long as n be greater than the larger roots of the two equations, right?
Mm-hmm.
So if you substitute C1 into this second term and the C2 into the first term here, you can solve the roots for these two equations, quadratic equations.
Okay.
Yeah, and then you find the larger roots of the two equations. You will find that n0 should be 2.
Okay. So this max is like it's comparing the is it comparing the two absolute value b and a, and then like the two square root?
Yeah. Not the square roots, but the two roots.
Yeah. Oh yeah. Two root absolute value c over a, right?
Yes. Oh, there should be square roots.
Mhm.
Yeah.
Yeah. It's two square root. Okay. So it's two on the outside. So it's two square root absolute value c over a.
Over A, yes. Yeah, I think you're correct.
So max will give you the bigger number between those two, right?
Yeah.
Okay. All right. Thank you.
Yeah. Okay, so where is this term from? Okay, so this term, so maybe I can try to explain that again here. Right. So because from these inequality to the red one and the blue one, this is no problem, right? From the above these two equations, we move the quadratic terms around. We will have the blue inequality and the red inequality. Okay, so the red inequality says that we want a quadratic function to be always positive, to be greater than 0. Okay, and because n can be infinitely big, so what if C1 is greater than 1? What if C1 is 2? Then this quadratic term becomes negative n squared plus 2n plus 1, right? So given this quadratic function, negative n squared plus 2 times n plus 1, how could it be always positive, right? Because there's a negative term here, and that n can be infinitely big. Then this is not doable. This is not feasible. So we must have 1 minus C1 should be greater than 0. The quadratic coefficient must be greater than 0, 1. Okay, so that's where the C1 is smaller than 1 come from. And to the second inequality, the blue quadratic equation should, the whole term should be smaller than 0. Then the quadratic coefficients 1 over C2 should also be smaller than 0, right? Because n can be arbitrarily big. And if n2 is smaller than 1, then this quadratic coefficient 1 minus C2 is a positive number. Then when the positive number is the coefficient for the quadratic term, then this quadratic function will be ultimately increasing, right? So we must have C2 to be greater than 1. That's where we have the constraints here. Okay, so these two figures are to help you remind what shapes a quadratic function may have. Okay. All right, so that's for the generic quadratic function case. So now let's look at a more general polynomial functions. Okay, so we are stepping into a more general cases. Say there's a general polynomial function in this form, which is the summation from A0 to AD, and the order of the polynomial term also increases from 0 to D. Okay, and we know that A are the constants, and the D's term has a greater than 0 coefficients. So in these cases, it is a more general case of the quadratic function case, right? So we should have the P of n should belong to the big theta of n to the power of D. Okay, and because n to the power of D is the highest order term among all these polynomial terms, we have we have 1 n square n cube until n to the power of D, right? So we should always consider the highest order term. Okay, and any constants that is degree 0 polynomial, then it can be expressed by this big theta of 1. This is something that we already used in the merge sort algorithm, in the merge sort analysis, right? We use big theta of 1 to indicate constants in our in a function. All right, so now let's quickly get into the big O notation. Okay, so the big O, the big theta basically bounds the function from above and below. But for big O, we only have a symptotic upper bound, okay? And that's the difference from big O and big theta. If we only know about the upper bound, but we don't know anything about the lower bound, then we can use the big O notation, okay? So officially, the big O of G of n is defined as this set, okay? And the constraint or the requirement says there exists a positive constant C, okay? Note that there's no C1 and C2, but only C and N0, such that the function is bounded by C times G of n for all n that's greater than N0. Okay, so there's no lower bound. There's no lower bound. There's only an upper bound here. So there's only one constant C involved here. Okay, so if we plot the relationships between f of n and g of n, it should be look like this way. Okay, if we look to the right of n0, then the f of n is always below c times g of n. And in this case, we call the g of n is an upper bound of f of n. Okay, so an interesting relationship between big theta and big O is that the big theta relationship f of n equals, so if f of n belongs to the big theta of g of n, then it implies that the f of n also belongs to the big O of g of n, right? That's straightforward, because when we include a tight bound, if we know the upper bound and lower bound, then of course it includes the upper bound, okay? And in another language, we will say, in other words, we will say big theta notation is a stronger condition than a big O notation, because it's in big theta there's two bounds defined at the same time, but in big O there's only one bound. All right. Okay, so this is a quite simple inference from big theta to big O. All right, and since we mentioned big O, let's look at the so-called tightness of the bound. Look at this concept a little bit. Okay, so in the language of set theory, we would say the big theta of G of n should be a subset of big O, because big theta is a stronger conditions. From big theta, we can infer that big O must be true, but merely from big O, we cannot guarantee big theta, right? When we only know the upper bound, we cannot claim that we also know the lower bound, okay? So for any quadratic functions here, this is an example. For any quadratic functions, f of n equals a times n squared plus b times n plus c, we can say that f of n is bounded by the big theta of n squared. This is a tight bound. We can have an upper bound and a lower bound, and also means that big theta the n squared is also the upper bound. Okay. And but more surprisingly, any linear function can also be described in big O of n squared. Well, if we plot it, that's not surprising, right? Because the quadratic function will grows very fast, but the linear function only grows steadily. So in theory, we can say that the f of the linear function, any linear function can have the quadratic function as its upper bound. Okay, but this upper bound is a loose upper bound. Okay, because this quadratic function is not the lower bound. It's just the upper bound, right? So we can arbitrarily draw an upper bound. If we draw a function that grows really fast, it can be the upper bound for any other functions, right? But sometimes the loose upper bound is not that useful. It's not an accurate estimates of the upper bound, right? It's an overestimation. Okay, when we want to know the running time of an algorithm, we basically want some accurate estimation. We want a tight estimation. We want a tight bound rather than a very loose upper bound, because the loose upper bound will give us misinformation. Okay. And now let's look at the tightness of the bound. So by f of n belongs to big O of g of n, we are simply claim that some constants multiply g of n is a symptotic upper bound of f of n, okay? But we didn't claim how tight an upper bound it is, okay? So in this case, the n square in green color, it of course is the upper bound for n, right? But it is not tight, okay? So there's some clarification I would like to make here, because in some other textbook, the big O and the big theta, they are sometimes used without distinguishing the meanings of them. But we need to stick to the way that we define big theta and big O here. So big O only described the upper bound, but it's not the tight bound. But if we want to define the tight bound, we must use big theta instead of big O. Okay, because you may have a chance to come into different ways, whether in the other books or in the online posts for algorithm problems. All right. So now let's finish the big omega notation before we stop our lecture today. So big omega notation, as we can guess now, we have dealt with the tight bound, the upper bound, then what's left is the lower bound. So it provides an asymptotic lower bound for on the function. Okay, the definition is like this, and similar to big O, we also need to define one constant c and one constant n0, such that the function uses c times g of n as the lower bound for all n's. Okay, and if we plot it, it'll be like this. So this time, the f of n is above c times g of n. It's opposite to the big omega. Okay, and also it means that to the right of n0, f of n is always above c times g of n. Okay, and it's basically a complementary to the big O notation. Okay, it doesn't look at the upper bound, but look at the lower bound. It basically tells how much running time an algorithm should cost at least. Okay, because it estimates the lower bound. Okay, so it means no matter what particular input size n is chosen, the running time on the input is at least a constant times g of n. Okay, so when we want to find the lower bound of function, we basically want to find the best case of the input. Okay. All right, that's big omega. And then let's put these three notations together. We will find that for any two functions, f of n and g of n, we will have the g of n is a tight bound of f of n if and only if we can prove the upper bound and the lower bound relationship. They are basically these big O, big theta notations, they are useful for analyzing any kind of algorithms. So if we talk about encryption algorithm, these are pretty timely, costly. They are not, well, speaking from running time, I don't think encryption algorithms, they are one of the most efficient algorithms. They are meant to be calculates very hard tasks. So, but they are still useful in describing any kind of algorithms, including the encryption algorithms. Yeah. So the plan for our course, we have maybe one or two lectures for special topics that we can talk about some special topics, including uh, uh, hash algorithms, and then the application of hash algorithms into blockchains. But we're not going to spend a lot of time on that. Um, I am not an expert on encryption algorithm, but as long as it is an algorithm, it can be based, as long as we need to know the running time of it, we can use the big O and the Big-Theta notations. Anyway, okay, so this theorem says that in order to prove the Big-Theta, we need to prove the big O and big omega. Okay, so we usually, by finding the lower bound and upper bound independently, we are able to prove the tight bounds altogether. Okay, so if we look at the insurgent sort, again, use the big bound, use the big omega or big theta notation, we basically can see that. So this is what I copied from the previous lectures slide. So if we put this notation, the T of n in this case here, in the best case, the Tj is 1 for each j, right? And the T of n is a linear function, okay? And a linear function can be written as a big theta of n. And in the worst case, Tj equals j, okay? And that case will give us a quadratic function, and it will give us a big theta of n squared. So if we put it all together, then we can say the T of n of the insurgent sort has the quadratic function as the upper bound, and the n square and the linear function as the lower bound. Okay. So the lower bound is not we cannot write omega of n squared to insurgent sort, because in the best case, it indeed runs faster than that case. Okay, so strictly speaking, if we want to describe the running time of insurgent sort, we need to use the big O, and the big O of linear function, big omega of n, and the big O of n squared. Okay, and typically, strictly speaking, we should not use big theta of n squared. Okay, but since the ideal case, the best case is not the most common one, so we basically can use. Sometimes it's also okay if we use big theta of n squared. Right, but this example to show that strictly speaking, we should not use big theta of n squared for insurgent sorts. Okay, so I think we are pretty much towards the end of this lecture, and there's maybe 6 or 7 slides left for the small o, and for some asymptotic bounds for some typical functions that we will use in this course. We will cover that in the next lecture, and in the next lecture on Thursday, we will also start talk about other the general type of divide and conquer algorithms. All right. I will release the quiz questions today and also upload the video later. Any questions, you can let me know now or in email.
I have a quick question.
Yes.
So regarding last class's quizzes, they didn't have any due date marked on them. Did you intend to mark a due date for them?
Yeah, I should have marked them in like 2 days, within 2 days. I probably forgot to set that because, yeah, some of the early quiz questions I forgot to set the due dates, but I will remember doing so for the future quizzes within 2 days.
So those quizzes are no longer available?
They are, I think. Can you try that? Can you see them now?
Yeah, I can still see them. I'm just asking, like, if someone were to complete them right now, would they be marked as late?
If it's past the if it passed the deadline, they will be considered as late. So the points of the quiz questions are to, as a test for you have listened to the lecture and you have gone through the chapters. You have gone through the course materials. And usually I would give a 2 days available time for each quiz question. Did that solve your question?
More or less.
Okay, so what is your particular question now? So did you miss the deadline for the syllabus quiz or the first quiz?
No, I'm referring to the ones from last week that didn't have a deadline posted.
Oh, okay, okay. Yeah, so that is my mistake of not setting a deadline. Yeah, I will set deadlines for all the future quiz questions. Thank you, Doug. Okay, so I will end the class now. Have a good day, guys.